Okay, sorry for the delay. We had some technical difficulties, but I think we are live on YouTube now. That's what matters. Okay. So let's continue with Johan. He will tell us how EFT meets CFT.
Okay, thank you, and thanks for the invitation to give this talk. Hopefully, I'll finish for some lunch. So I wanted to just make a. Can I move this? To begin with a very quick 1 minute pitch about what we're doing in this project. So this project is based on some work with Stefanos, who's here, and then Franz Herzog and Jasper Rosman and Epfe. So we all know that renormalizing lambda phi to the 4 theory to leading order is a textbook exercise. You can compute the beta function. It has this minus epsilon term plus higher orders in lambda. You can compute the fixed point, lambda star, perturbativity in epsilon, etc. And this should somehow be related to the Ising CFT in 3 dimensions. And of course, since then, people have computed a lot, and in particular, the leading operators phi, phi squared, phi to the 4, related to the leading critical exponents, are known to order epsilon to the 7 in ON symmetric case, and to order epsilon to the 6 for a general coupling lambda ABCD. But in the bootstrap or axiomatic approach to CFT, we also care about subleading operators. And we have this idea that all operators in the spectrum are needed to make the theory self-consistent. So there is this picture here from David Simmons-Duffin's paper of some of the low-lying operators in the 3D Ising CFT with an axis of spin and dimension minus spin. So all of these are numerical data, and it would be great to have access to also perturbative predictions for these operators. So we would like to have multi-loop results for composite operators beyond just these leading few. So typically, these operators here are constructed with many fields and many derivatives. In order to do this in a systematic way, it would be nice to have a way to write down bases of operators, generating all the Feynman integrals, evaluate them, all like in a manageable way. But turns out that there is a research field that has done exactly this. So this is the field of effective field theory. And in our work, we are collaborating with people from the effective field theory community. So this leads to our set of results, which is order epsilon to the 4, epsilon to the 5 results for all composite operators with dimension up to 6 in the free 4D theory and spin up to 2. And we do this in an arbitrary lambda phi to the 4 theory, so with this type of arbitrary coupling constant. So I will come back to the results. Well, first I will show this is again an overview of the results. So here we're doing up to spin 2. At spin 2, you can also have symmetric or antisymmetric Lorentz indices, so we consider both cases. And here's just a sample of our new results and typically what's known in the literature before our work. Of course, this depends on which theory you look at. More things are known for Ising and ON, as I try to summarize in this paper. And in hypercubic with Stefanos and Bednyakov, we try to gather a lot of data and compute a lot of data for hypercubic. But for other results, there are even more sporadic results. But our main point is we can now, thanks to these recent techniques, improve quite a lot of compared to the previous orders. So my plan is to explain a bit what this is EFT and EFT community. Then discuss two key features, which actually have a surprising similarity with what we're doing in CFT. Yeah?
Since you mentioned antisymmetric, what's the expectation when it's take epsilon 1 there?
They should just exist. So this would have 2 antisymmetrized Lorentz indices. So if you go to 3D, you can like eat them with an epsilon tensor. And then you have 1 Lorentz index left, so you get like a parity odd operator in 3D.
Exactly.
A parity odd spin 1.
So but that maybe has another representation. It looks like if you start from 4D, you could have different representation of the same operator, and I'm wondering if there is a prediction that the same dimensions then need to coincide technical one.
I think there is a unique formalized epsilon pre-image of each operator in 3D. You cannot do parity odd across dimensions. You can do other things in 4D, say a parity odd vector in 4D would continue to something else in 3D, a parity odd scalar.
Can you leave the door open, please?
Okay, so this is my plan. Yeah, so both in the case of operator basis and the case of computation of anomalous dimensions, these are actually key elements in both our fields, and we have direct similarities here. So I will discuss these two things in a bit of detail and then come back to our paper at the end. So what's EFT? Is some very simple picture. And EFT is a theory which we introduced when we consider very different energy scales in a system. So we might have a high UV scale that is not very important when we consider physics at low energy. So we might have some masses, some particles, or a typical energy scale that we do a scattering experiment. And in theory, we can write down a low energy quantum field theory with their normalized interactions, and then a sum over higher dimensional operators, which would then enter with a natural scaling with this cutoff. So bracket O here is the engineering dimension of the operator. And within this EFT, we can compute observables. They will be given in terms of the renormalizable parts and also in terms of these coefficients CI, known as Wilson coefficients. And if you introduce a few of them, you start to get corrections in 1 over lambda, and you can kind of make a manageable series expansion in 1 over lambda and get predictions using the EFT. So there are kind of two main philosophies you can take. One is that we're just interested in low energy physics in general. We can parameterize all our observables just in terms of a few of these CI. Or say if we're doing collider experiments, we can take the renormalizable part as a standard model and then parameterize physics beyond the standard model in terms of non-zero coefficient CI. So this is the kind of textbook example of an EFT, which is also a historical example. So long ago, before we could do experiments at high energy, people were modeling, say, a muon decay by a contact interaction. So this would be a high-dimensional operator. This operator has dimension 6. It contains the muon field, electron field, and some neutrino fields. But we know that as we approach the energy scale of the W boson, this point-like interaction is resolved into exchange of a W boson. And if you work in energies around lambda or above, you don't really need the full theory. And if you have access to the full theory, you can integrate out to this W boson and derive a prediction for this coupling constant. So EFTs, now I'm at CERN, so I'm learning a lot about this from my colleagues there. So EFTs are really central in what we're doing in particle physics in general. And there are many different EFTs suitable for certain energy scale, low energy EFT, standard model EFT, chiral perturbation theories. There are also EFTs you can develop in when you have kinematic parameters. So there might be certain kinematic subregions which you can develop your own EFT for. This would just be like effective theory. So this picture I stole from the internet, just to say a whole set of EFTs you need just if you want to study QCD. And there are also different, this is really a standardized topic with different lecture notes and textbooks. These are a couple that I've been looking at. So that's about EFT. So now I want to discuss the idea of operator basis. And it turns out that EFT people use exactly a conformal primary basis. So imagine we want to search for new physics in beyond the standard model. We would have lambda at some scale above the TV scale. And we would write down the full standard model and try to construct high dimensional operators. Here I organize them by dimension, and also at each dimension you need to write down a full basis of operator. In general, this is a difficult task. The number of operators, even just singlet and scalar operators, which you need here, grows really fast in these theories. And people have done very systematic lists of operators and try to agree which is the best one to use, etc. So this is the famous paper from 2010 introducing what's known as the Warsaw basis for dimension 6 operators. But the question that was nagging people for a long time was like, how do we know we have a complete list? There are many redundancies in the list of operators. So this was resolved in this paper with the title 2, 84, 30, 993, etc. High dimensional operators in the SMEFT, which found a systematic way to derive these numbers and at least the field content of these operators that you expect at a certain range. And this is also could be very relevant for CFT. So I want to give a bit more details on this. This is known as the Hilbert series or character counting. And of course, if you're in CFT, you expect Dolan and Osborne have worked on this type of things earlier, and this is some paper by Dolan. So we're asking the question, how many conformal primaries are there at a given dimension and spin in the free theory? So for instance, if we consider a single scalar field, we'd like to see the operators phi squared, phi 4, etc. that we know exist. But we also, if you worked a bit harder on building free theory operators, you know that there is no primary operator with 2 derivatives and 4 fields. So we would like to see this coming out of our counting. So there are a few ingredients you need to implement. Say in Mathematica, you consider representation theory of SO4, which is like SU2 times SU2. So there are 2 spin labels, JJ bar. Write down a character for a conformal multiplet, which knows about the spin and the tower of descendants, etc. The character for the field phi is a bit special. So Q here is kind of counting the dimensions. So the character for the field phi is a bit special because it lacks a derivative. We know that del square phi is 0. So it doesn't have all the descendant expected. So that's why it has this 1 minus q square factor. And then from these characters, one computes what's known as the Hilbert series. It's kind of a partition function for the point of view of counting, which is given by this fancy plethystic exponential of the character for phi, which is our building block. And here I also inserted an extra power counting just to keep track of how many fields we have. And if you want to have global CMERGE, you can also introduce the character for the fundamental in your representation. And the plethystic exponential is just taking everything, replace all ingredients by their k powers and summing them and exponentiating them. So if you go out and do this, say for the free scalar, you just implement the ingredients. You start expanding back in Q. And then you can start to match with the characters of individual operators. So we can see here at the level of one single field phi, we just have the character for phi itself back. And then that actually takes care of this whole thing. And then we get the next point, which is phi square. This is like dimension 2, spin 0. Then we have dimension 3. At dimension 4, we have 2 operators. We have one which has 2 fields and spin 2, which is the stress tensor. And then we have the phi to the 4 operator. And you can continue and read off the spectrum in this way. There's also a method in which you can take this whole partition function and integrate in x and x bar to project only onto the scalar contribution. And then you can start to read off a bit higher in the spectrum the set of scalars. So this tells us, for instance, here at dimension 8, we expect 2 scalars, and they should have either 8 fields or 4 fields. So this would be phi to the 8 and del square phi to the 4. But at dimension 6 here, we don't have this operator with 2 derivatives and 4 fields. And this counting, of course, agrees with what you would get if you try to explicitly construct primary operators. But this becomes very tedious after a while. Now, OK, so this is kind of perhaps familiar to you, because this is exactly what you do in CFT. So now I want to explain briefly why.
Yeah, so it's actually not clear why Yamaha get any credit for doing this trivial itself.
Well, it was quite non-trivial to do it for the whole standard model. But indeed, I think this is a sign of not enough communication across the field. Because in the EFT community, this was a great breakthrough, and everyone cites this work, right?
But it's a totally trivial that has been known for time immemorial by Dolan et al.
Yeah, but they didn't do the standard model. So, yeah. But OK, so why is it that this primary operator primary operators are also important for EFT? And we actually mentioned in a question earlier, but redundancies in the Lagrangian. So there are two ways to see, for instance, that this operator does not exist. One is that you can do field redefinitions in the Lagrangian. Here I choose a particular form of this, phi cubed box phi. And if you take, say, just a free scalar perturbed by these two high-dimensional operators, you can do a simple change in the field phi. You're going to get what you have from before back, and then you're going to get some overflow from here. And in particular, this overflow contains some boxing coming from the kinetic term, the mass, etc. And then you can repackage this into a new Lagrangian that just is free from these type of operators. So these operators are known as redundant operators, and they can be removed by field redefinitions. And this is at the cost of changing some of the other constants, for instance, these lambda constants. One can also see this on the level of the scattering amplitude. If you just naively compute the 4-point scattering amplitude with this first Lagrangian, you will get this box turns into p square, and you would get sum of all momenta square, but each momentum square is just mass square, and you would exactly get a constant back, which is what you would get if you computed the 4-point scattering amplitude with this shifted Lagrangian. And of course, you can just try to write down the number of independent terms in the scattering amplitude. If you worked on like Bootstrap of effective field theories, this should all be familiar. So here we have write down the scattering amplitude at tree level in terms of Mandelstam variables. And then you write down the most general polynomial in Mandelstams you can, keeping track that s plus c plus u is 4m squared. And then here, which corresponds to dimension 16 operators, is the first place where you can write down two independent terms. So we expect two phi to the 4 type operators at this level. And again, this is what happens if you use this Hilbert series or partition function method. Yeah?
Probably this is obvious if you use cosine symmetric variables. Can you use a different formula to count this structure? What I'm trying to say is that I don't know. Yeah. From the amplitude point of view, that's totally obvious to me. Like these structures, how to count them, and how many appear.
Yeah, well, maybe it's easy for a single scattering amplitude, right? If you were to write down all amplitudes in the standard model, it's a bit harder.
Yeah. Okay.
Also, you need high point amplitudes. I mean, this was just a simple exercise for 4-point. So in summary, the conformal primary basis is what's needed in the scattering amplitude as well. And we used to the fact that there are 3 types of operators. We have primary operators, descendant, and redundant operators. And we used their description in terms of CFT. But also in the EFT, now we can understand these type of operators. That the primary ones are those that contribute to the S matrix. The descendant operators actually are non-trivial due to momentum conservation, and the redundant ones are those that can be removed by field redefinitions. Okay, so part 2, here I want to explain why computational anomalous dimensions are important in the effective field theory. So this is a very nice picture that I also stole, which is kind of the main businesses if you want to use effective field theories, say, in searches for new physics. You might first write down some interesting model for new physics. You integrate it out, and you find the coefficients of high-dimensional operators that you get from integrating out. This is at a high-energy scale. But then we might do experiments at a low-energy scale. And to match between these two scales, one needs to do what's called running. And then finally, one compute observables at this lower scale. So running is the fact that these constants actually change with the RG scale. So there is a Kalan-Sivansky equation for these constants. And the leading term here is the anomalous dimension matrix, which is exactly the same as we have in conformal field theory. And then there are higher order corrections. So if there is in a very simple case where there is no mixing, so we just have a single operator and a single coupling constant, say alpha strong, Then you can immediately integrate this equation, and you can see what is the change of this EFT constant between two energy scales. It's given as a scale of the coupling constant, as a power of the coupling constant ratio, with an exponent that's this anomalous dimension. So why do we need to do this running at all? Why can't we just use this CI of lambda for our computations? And this is in a very schematic way, because when we do computation in QFT, we need to fix an RG scale, a cutoff. Well, not a cutoff, but an RG scale mu. And typically, observables are in power series in your coupling constant, but also involve logarithms in momenta. And these need to be regulated with this dimensionful scale mu. So unless our momenta are close to mu, these logarithms could become very large. So we want the logarithms to be small to get a good convergence of our power series. So then after we've done some magic computation, we need to run down these constants, and they can change quite substantially under this RG flow, all the way down to our experimental scale. I will give some more EFT references on this running later, but typically these two businesses, matching and running, is occupying a lot of people. And for the matching, just as an example, people have developed real serious software to do this. And the phenomenological goal for, say, standard model is to have one loop matching, which is what this software are doing, and two loop running, which is under progress. So two loop anomalous dimensions. Okay, so now I want to come to our paper. We're actually writing two papers. We finished one paper last week, which is very short, but has the summary of our results. So again, we compute for, this is the 3-level dimension of the operators, and we compute for spin 0, spin 1, spin 2, typically at 5-loop order. Then we pushed a bit higher for Z2 and ON symmetric theories, also some high-dimensional operators. And then we're planning to write a longer paper, which contains this title also of my talk, where we explain a bit more in detail what we're doing, and in particular focusing on extractions for various conformal field theories. And this is what it looks when we start to write down just the operators. So here I want to emphasize that we consider the most general coupling here, and also the most general form of these operators. So in the step 1, we derive general results for these operators. So we generate the Feynman diagrams, we evaluate them, all of this on the computer, of course, using some cutting-edge method developed by these collaborators. And all of these are available on a GitHub repository. So in principle, you can just download them and then extract data for your favorite theories. So this is step 2. And what you do in practice is that you then take these general operators and the results written in terms of these general indices and project them onto tensor structures compatible with the global symmetry you want. So I want to give a few examples for what we did. First is the Ising CFT, which we already heard about earlier this week. So here we have perfect knowledge for the Bootstrap. We have precision island, precision spectrum. We also have some spectrum across dimensions. So here is a plot with the numerical data from these papers. So each dot here is numerical extremal functional method results for space-time dimensions between 4 going down through 3, where we have Simons-Duffin's result, and then onwards a bit. And here I have overlaid now previous perturbative results and also our new perturbative results here. So we see that they improve quite a bit compared to the previous lower order results up in this region.
This is after resummation?
This is after resummation. So the resummation, we do a very simple resummation, which is a Padilla approximant. It's just a rational function in epsilon.
From 2D to 4D? Two-sided?
No, one-sided. One-sided.
Without Borel?
Without Borel, just a simple Padilla. I mean, here is the formula. Okay. So earlier I was writing a database of all known data in the Ising and ON CFT. So now I'm we're planning to release a new version of this with all these new data included. So you can load easily the dimensions, say now the third even operator, so this red guy here, known to epsilon to the 5, and then you can just do a Padé approximant. Mathematica can do it for you. And then you get the numerical value here, which can be compared with this black dot here from David's paper.
Is that dimension 7 operator seen by the fuzzy sphere?
No. It's also, David has some operator up here, but there's another operator coming down from above, and it's not really clear what's the interpretation of this. He has some result at like 8.2 or something. I don't think fuzzy sphere has it. Okay, we can also do ON, or here is example for O3, where we again have a precision island for the Bootstrap, and this author has also shared some unpublished data for the spectrum in this precision island. So we,
Sorry, I'm missing something.
yeah.
You went from counting things. So you told us how to count,
Yeah.
which we knew, and then you gave us some results for very high loop anomalous dimensions,
Yeah.
which I think is a hard thing, but you didn't tell us what you did. That was that went from counting to computing.
Yeah. So what, I mean, in a sense, conceptually, we're not doing anything new. So what you do when you want to compute an anomalous dimension, you insert the operator in correlators. You compute these correlators. They have some divergences. You cancel the divergence with counter terms. You extract these Z factors. You take the logarithmic derivative of the Z factors. You get the anomalous dimensions. OK, that's QFT standard. Now, to do this with all these operators, with all these indices, we need to have some purpose-written code to do this effectively. And this is what our EFT collaborators have already developed. So we have adapted these codes to deal also with operators with Lorentz indices. And so you run this code. It takes hours. And we compute anomalous dimensions of all these operators to 4 or 5 loop in lambda. And then, of course, after you have them in lambda, you can go to the critical coupling and get CFT data.
Sorry, Johan, in particular, does the matching and running have a relevance for this part? Or will it,
So matching has no relevance for us. Running, to do running, you need to compute anomalous dimensions.
yeah, so in that sense, so you're okay.
So the computation is done. Then you can use it for running. I mean, this is scalar theory, so it's not so phenomenological, but you can do running in a scalar toy theory for new physics. Or you can extract it for CFT.
Okay, thank you.
And as far as we know, this is, again, basic QFT. Of course, you could do this in the 70s. But since then, a lot has happened. A lot of technology has developed. And now we're trying kind of connect these two applications again.
And just a comment to add, like, oh, sorry. EFT people up to now didn't know that we really care about this stuff.
Yeah, and we barely knew that they had 5-loop technology.
Hmm?
What a benign community.
Okay, yeah. So 03. So now with this picture, I want to show how good understanding we now have of the low-lying spectrum of the O3 CFT. So here is our new data, again with Padé approximants coming down from dimension 6, 5, just in the scalars. And there's a lot of Bootstrap data here in many different representations. And I mean, the agreement is quite remarkable in my opinion. And then we also have our spinning operators in this table. And we, at a few places, improved the loop order by quite a lot.
What is the, what can you explain exactly what corresponds to what with the dotted lines in this figure? And what is this weird shift that happens close to?
Yeah, okay. So I didn't want to put the dot straight on at 1.0 here. So I put a little dot to the side and then a thin line towards it. But yeah. If you have better ways, this is for the future work, so we can redo the picture if you have nicer suggestions. You mean here? Yeah. I mean, it's still in the ball plank. Actually, this one comes from above, so it's only known to epsilon to the 1 anyway. But then there's also a missing one here, which I think just has not been found in the Bootstrap or Monte Carlo yet. So, and of course, we can. Doesn't need to be perfect, right? This is non-perturbative results.
Yes, you did emphasize that it's EFM data, so it can be a bit off. There's nothing wrong with that.
Yeah. I didn't, but now you did.
Sorry, and you expect typically that higher dimensional operator would be less precise also from epsilon expansion?
Yeah, probably. Less precise in EFM, probably also less precise in epsilon expansion. I mean, we don't have so much data until now, so. Then, okay, so these are theories where we know. Okay, so this is just the spin 1 and spin 2, similar picture. These are theories where we know very well. We have this tiny Bootstrap island. We also applied this to the hypercubic CFT, which is the CFT where you get where the coupling constant has two. The coupling has two coupling constants with different tensor structures. And the second one here breaks the Owen symmetry to the hypercubic symmetry. So here we already did some perturbative spectrum analysis earlier for specific operators, but now we have this larger set of operators. And as you will learn more this afternoon by Stefanos, these new results that we have here are actually important to provide gap assumptions for the Bootstrap in if you want to study this. In particular, it's been very hard even to find any even large island for the cubic CFT, and what Stefanos and Andreas Stergio managed was to find an island of this shape, at least partially, thanks to some of our new estimates. So, okay, I don't know how I'm doing with time because we were so delayed, but this is my last slide. I wanted to highlight some recent work on the EFT side where people have done not just scalar theory, but in the same idea, to put the most general theory with all field indices as general as possible. People have done that in a generic 4D theory with the scalars, fermions, gauge fields, etc. I think this Lagrangian here is the best to illustrate what they do. This is the normalizable part, so operators with dimension up to 4. And then on top of that, you add EFT operators. These guys are concerned with dimension 6 mostly. But I think these are interesting starting points towards studying other classes of QFTs and therefore maybe CFTs. So we could consider 4D gauge series, like with various degrees of SUSY. We could try to do some epsilon expansion for 3D theories with fermions or gauge theories. And then, which requires a bit more leap to develop new diagram technology in other space-time dimensions. We could also try to study multi-critical models, which have phi to the k marginal interactions. So they would have all different upper critical dimensions. But I will stop here. Thank you.
More questions?
So can you use this technology to study the large charge limit of operators with spin in the O2 model, for example?
Well, so the large charge limit, this means essentially the dimension of the lowest operator of a certain charge, so certain charge under O2. And yeah, I mean, if you, oh no, this doesn't work yet. So essentially, this would be the O2 version of some of the operators in this picture. So already here are some operators. These T3, T4, T5, etc. are essentially the charge Q operators. And the lowest ones here we have. So if you want to do this, to say higher charge, you just need to consider high dimensional operators.
Okay.
Now for these particular ones, they all follow a pattern where their dimension is a closed forming queue. And people have already guessed this closed forming queue, I think at order epsilon to the 6, so they're already beyond what we're doing. But maybe they're also spinning charge sectors where there is less results. So, I mean, conceptually everything is possible. Then it's a trade-off between computational resources and interest.
Okay. Thank you.
Yeah.
I mean, is there like a result of like how to count operators with like gauge fields, like counting the primaries?
Yeah. This is exactly. I mean, this is what they did for the standard model. That's the gauge theory.
I mean, SMET people have done it, but like I'm wondering, like, okay, so we can just borrow the result pretty much.
Yeah, you can just borrow the result. You can read. I mean, I wrote these characters for the scalar multiplets, but there are similar multiplets, and then there's a way to remove to go to gauge theory singlets.
I see. What about monopoles? Is there?
The monopoles are
Like QED3 there.
That's non-trivial.
Yeah.
Yeah, because they are not local composite operator. I mean, they are local operators, but they're not local composite operators in the Lagrangian perspective. So, I think there you need to do something smarter.
Yeah, I mean, like from large N, we can construct some of these monopole operators or like monopoles with some fermion excitations, but like there's always this question mark, like what operators do exist and what operator we actually have to remove. Yeah, it'll be interesting.
Yeah.
Right.
Yeah, I cannot say anything too concrete there.
Thank you.
Any final question? Okay, so if not, let's thank Johan again.